All right, folks, we are going to fill in the rest of the notes. So, first question: what is the difference between statistical and practical significance? And we're going to refer back to this XKCD comic. So, the idea here is that statistical significance is you're following this technique that we've learned, and if something is statistically significant, all it means that you have found something where the p-value, if the p-value is less than the alpha level, then you have, using this technique, right, you have found something that, by following the technique, is statistically significant. Okay, so that'll be something where p-value is less than the alpha level that was set. Something that is practically significant is something that is actually useful and honest and usable, right? So the example we have is this XKCD, and I'm going to ask you as part of homework to explain what's going on here, but we're looking at, do different colors of jelly beans, the candy, cause acne? So they investigated it and they found no link. They had a p-value of more than 0.05, and they're like, okay, we're done. And then somebody says, well, but I think it's a particular color. So they go through and check every single color. So they find, no, it's not purple jelly beans, it's not brown, it's not pink, it's not blue, it's not teal. And you have to read these very carefully. But I think they find one over here that is significant. They even distract the guy who's playing Minecraft. They find that green jelly beans do cause acne. And the question is, and everything else is a no. Right? So they have done 20 hypothesis tests. They found one, and then now they're like, okay, I found something that's worthy of a headline: green jelly beans cause acne. So the question is this actually useful and honest? And the first answer is going to be, this is not honest, because they didn't have an idea in mind when they did the study. They were looking for a significant result, and they just kept trying colors until they found one. So that is not how you do this. That is how you are really, really shady. That is searching for something significant. It's not meaningful, because that's not how they started the study, right? Started the study by just saying any color, and they found that it wasn't significant, and they should have stopped right there. So if you run a test 20 times and find one, that's just not, that's not how we do it in the science, right? So what is the problem of multiple tests? It's going to be honesty, shadiness. The idea is you have one idea, you write your hypotheses, and then you get your data, and then you find the answer to your question. And if you don't have hypotheses in mind and just look for a significant hypothesis test, you're not really keeping with the spirit of the idea of what we're doing. Okay. Next up, we're talking about type 1, type 2 errors. And then heads up, guys, we're working with this potato chip example that's on page 565. So I'm going to walk you through this data set and explain what these graphs on the next page are about. I'm really sorry, I tried to find a really cool app to model this for us, but kind of not working right now. So the idea of power is the ability of a test to correctly reject the null. Okay. The ability of one honestly come by hypothesis tests to correctly reject the null when that is the right decision, right? So when that is true. So you were not expected to calculate the power test on the AP exam, but I will show you how you can do that. You need some special information present to be able to do it. So it's not something you're just able to do whenever. So power of a test. The big thing you need to remember, power of a test is 1 minus the probability of a type 2 error. So it's 1 minus beta is power. So that's really the one thing you need to kind of keep in mind for questions that will ask you about that. So in the potato chip example, the idea is there's a truckload of potatoes, and if the entire truck is 8% blemished potatoes that are not good to make potato chips out of, you would send them back and ask for a new truck of potatoes. So the null hypothesis. So now they're telling. So the magical number that you need to know to do the calculation of power is. And by the way, you know what, guys? I'm going to change this one to 11, because that's what it is in the example in the book. So the question is, what if the actual true proportion parameter is 11%? So what if you have a truckload of 11% blemished potatoes? What is your ability to correctly decide that this truck should go away, right? So what's the power of the test is the ability to look at a truck of potatoes, take a sample, and decide correctly that this truckload is bad, right? That you really don't want to make potato chips out of it. So we should reject the null, because the true proportion of blemished potatoes is in fact bigger than 8% blemished. It's 11% blemished, right? So will the inspector be more likely to find convincing evidence that the truckload is bad if he looks at a small sample of potatoes or a large sample of potatoes? So one way to think about this is, if you have a small sample of potatoes, you're going to have a larger standard deviation, which means your graphs will be wider, right? So let's say there's the graph of if the null is true, numbers you would expect to see. So that's going to be a 0.8 in the middle. And then there's going to be the graph that you're going to add on top of that of if the alternate is true. Now, we happen to know the alternate. We happen to know the true proportions. The only reason I can do this problem is I can figure out what to sketch as the center of my next graph. So the actual proportion of blemished potatoes is 11%. So these two graphs have different centers, but they should be the same graph. So it's the same graph repeated. So I'm going to try to draw a graph of the same size. All right. So the question is, here's your overlap. Right? Let's say you're doing an alpha is 0.5 test. So that would mean that if the upper 5% of your blue graph is where you're at, you should be deciding to reject those potatoes. Right? So on the blue graph, this is blue shading, right? Let's say this is my alpha, which is 0.05. Now, wherever this number is, this is going to be your cutoff value. This is going to be the p hat that you get from your sample, at which you will for sure be deciding that this truckload should go away. So if your sample proportion is this particular size or more, you're going to reject the potatoes. If your sample proportion from the potatoes you inspect is less than that, you're going to be failing to reject. We stuck on the blue graph of these potatoes are fine, right? If we know that the truth is that actually 11% is the middle of the graph, we know that we're not really on the blue graph. If you get this proportion of blemished potatoes in your sample, which is less than 11%, the way I drew it, the chance of a type 2 error in this graph is this one right here. This was your alpha, this is your beta. The chance of accidentally deciding this truck is fine and it should go. And you're going to try to make potatoes out of it, but have like a lot of potato chip bags that are just not sellable. Right? This is your chance of making an error and accidentally deciding this truck is fine. However, the white space on my other graph, this is the power of the test to correctly send the truck away. So the power is this part. So this is, if this is my sample that is small, I'm going to have a fairly wide graph. Okay. Now, if I try this again with a larger sample, so I'm walking you through this visually because I want you to think about these areas on the graphs, but you can easily, this question is, you can answer this question faster than what I'm doing. I'm just giving you the slow version, all right? So heads up, I'm measuring how far apart the centers of my graphs are because I want to repeat the same thing over here. So 0.08, this was an inch apart. Okay, so this 0.11 is in the same spot. However, this time, if I have a larger sample, I'm going to have a much smaller standard deviation, which means these graphs will be skinnier, right? So what I'm going to do, I'm going to sketch a skinnier graph for this sample. And I'm going to sketch the same width graph for the if the alternate is true graph. All right, so those are about the same. So these are not, right, so this is small sample, wider sampling distribution, large sample, smaller sampling distribution. So we're going to look at this overlap again. All right, and then heads up, guys, the cutoff region is going to be in a different spot. Right, so I am shading 5% spot on this graph will be further away. Will be close. Actually, yeah. So the 5% shaded spot on the blue graph will be further in. So I will be able to reject the potatoes at a smaller p hat. So here it was closer to the 11%. Here it's kind of in the middle. So this is going to be 5% shaded. This is my alpha level. I will be able to tell the truck to go away at a smaller p hat on this graph than I would on this one. And what that means, what the consequence of that is if you look at the black graph, there's way less overlap between the two graphs, which means that my chance of a beta, a type 2 error, is way smaller. And because my chance of accidentally telling the truck to stay when the potatoes are bad is way smaller, what's happened is the power of my test to correctly reject a truck of potatoes, the power is much bigger, right? Because I've shaded way less of this, my power has increased. So we're going to say the beta level dropped because there's way less overlap in these two graphs, which means that power totally went up. So sample size will increase your power because you will be able to reject the potatoes at a smaller sample proportion. So that is a very, very, very powerful tool, right? Sample size is the best tool you have. Sample size bigger, less type 2 error, way more power to correctly reject your null. Next question, will the inspector be more likely to find convincing evidence that the potatoes are too blemished, send the truck away if he uses a different alpha level? So the idea here is that if the alpha level goes up, then the type 2 error will immediately go down. Basically, guys, what we're doing here is moving this line. So if the alpha level goes up, I'm going to shade more blue, which means I will automatically have less black shading, which means less type 2 error, which means power immediately goes up. So your highest alpha level will have the most power if you can't change anything else about your study, if you've already picked a sample size. If your alpha level goes down, then your type 2 error will go up and power will decrease. So this is not as strong an effect as the sample size effect, right? This was kind of a huge improvement, but the idea is I can mess with where this line is on my graph. So if the alpha level is 10, I'm going to shade way more of the blue graph, and I will immediately be shading way less black, which means type 2 error down, power is going to include this bit that I couldn't use when my alpha level was so high. If I go to an alpha level of 0.01, I'm going to have to be shading way less blue, which means I will automatically be shading more black. So my type 2 error is increasing and my power is decreasing. Okay, there's one last tool you have for changing your power that is super shady and really never ever going to happen. But let's just talk about it for one moment. The last situation here is that suppose you have a second shipment of potatoes and you magically know that 50% of these potatoes are blemished. So your chance of getting a sample from a 50% blemished truck is going to be much easier to notice that there's too many damaged potatoes in this truck. So the idea here is that your last tool, which you really never have, is that if your null hypothesis number, in this case, that's the 8%, but your null hypothesis number and your actual population parameter are very far apart, in this case, really far apart compared to the graphs we had earlier. So if it's really 50% bad potatoes instead of 11%, these graphs are so far apart that if I pick any alpha level, right, the amount of this graph I'm shading accidentally over here is basically none, right? So the beta level, the type 2 error will be tiny because what I've managed to do is separate the two graphs. So a visual trick is if you separate the graphs really far apart, the amount of overlap is very, very low. So this is called effect size, how far apart your null and the actual population parameter are. This is not really a tool you have. This is not really something you can change if you're doing the study. But if the null and the actual parameter value, should you ever know it, which you won't, are far apart, then the beta, the type 2 error is very, 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 very low, which means power is high. So if you have a 50% blemished truck, much easier to decide the truck should go away than if you have an 11% blemished truck. That's the idea. Is there anything else that affects power? Totally not part of this course, but the type of sampling can affect power, which is we are not something we're going to be able to do. But for example, a stratified sample gives you more power, but that's not something we will talk about in this class. So your major tools for actually making changes in your study, right? Your actual tools as a researcher are, number one, big sample size, huge increase in power. And if that's already done and you've got your data and you can't do anything about it, increase your alpha level to increase your power. So those are the two tools as a researcher that you can do to make the power go up. Yeah. So suppose that the true proportion of blemished potatoes is 11%, like before. If the alpha is 0.5, the power of the test is 76%. What does this mean? This means that your chance of correctly rejecting the null, in this case, rejecting the entire truck of potatoes, is 76%. Your chance of correctly rejecting the null, telling the truck to go away, is 76%. So there's a 76% chance of correctly rejecting the null when the alternate is true. You have a 76% chance of correctly sending the potato truck away to empty the potatoes and try again. That's what it says in the notes that I have over here. You're like, if in fact the truck is bad, your chance of deciding the truck is bad is 76%. The other thing I put on here is beta is 24, right? Power plus the chance of a type 2 error add up to 1. So 76% chance of rejecting the potatoes means 24% chance of bad truck, but you don't notice it's a bad truck. So that's not great. Okay. What is the probability of a type 1 error for this test? Oh, what I just said. So the formula is power is 1 minus beta, or 1 minus type 2. So if we switch this equation around, it's also going to say chance of type 2 error is also going to be 1 minus power. My dog is doing a singing song for you. Okay. So 1 minus 76%, 24%. Interpret this value. So if the truck is bad, which the definition here is too many damaged potatoes. Dog, sing, stop. Okay. Too many blemished potatoes. Your chance of accidentally getting a sample that doesn't tell you that, of accidentally keeping the truck, keeping the potatoes that you really don't want to, based on your sample, is 24%. So this is kind of basically what you need to know for AP tests. You don't really need to know how to calculate it yourself. Right? In the Benford's Law and fraud example from a while ago, is this company faking its records? Suppose that P, the actual proportion of records at the company that are starting with the digit 1 is 0.25. 25% of all the records at this company begin with a 1. When the alpha is 0.05, the power of the test is rather low. So we're going to say there is a 58% chance that the person doing the test, the hypothesis test, a chance of correctly rejecting the null, which would be deciding that there is fraud when there really is. This is not great. This is a very low power. How can the company increase the power of their tests? Well, number one, sample more records. Increase their sample size. Way huge effect on their power. Sample more records. This has the biggest effect on their power. If they can't do that because they've already been over at the company and grabbed all the records they wanted, then the other option would be to raise the alpha level. The alpha level currently is 0.5, so it's going to raise the alpha level to an alpha is 10. But if they can do the first one, that would be the recommendation. Okay, for what values of P would the power of the test be greater than 0.58? So again, this is about the graph overlap. So if the null hypothesis was on the right side this time, so it's 0.301 is there is no fraud percentage of records that start with a 1. For what values of p would the power test be greater than it is in this situation is if the two graphs were further apart. So the 0.25 is below. So if the population proportion of records that don't start with a 1 of the company is further away from the 0.301, if the graph moves to the left, that would increase the power. So we would want to move the graph further in that direction. So if this is less than 0.25, that will increase the power. So should the company have fewer records than 25% start with a 1, then the ability to notice that there's fraud will increase. So drag the graphs apart is the comment.